4.6 is on friction. Now, friction is quite complicated. We've sort of ignored it for the last few months or so. A lot of problems that we ignore air resistance, um, don't consider the friction when the ball's rolling, things like that. But it's important because it's always present when you have two surfaces in contact, whether those surfaces are of a ball and air, or car wheels on a road, or a runner sliding in to second base. The friction is there. And in fact, we walk because of friction. Um, and so it's without friction, we'd be unable to walk. We would just be standing in place. But friction is very complicated because it involves two surfaces in contact, and those surfaces are highly variable. And it depends on how fast the objects are going. It depends, and as they travel next to each other, they heat up more. So there's things like that. So it's quite complicated. But two things that we can say about friction are, one, it is always present. Sometimes we ignore it. We always have to simplify it to be able to analyze the problem. That goes back to when we discussed models and simplification. And two, it is a force. That always acts to oppose objects sliding past one another. So it's always opposite in direction of motion. So if you have a block sliding on a road, the friction force would be that way against its motion. If you have a block going down a ramp, the friction force is up the ramp against its motion. If you have a ball falling through the air, the friction force is up against the motion of its fall. The amount of friction you get between two objects is proportional to the amount of force pressing the two objects together, okay? But critically depends on the material the surfaces are made from. So what we have here, since it's dependent on how much is pushing on it, well, you might recall that if we did a free body diagram for this block right here, well, we would have the forces of the gravitational force, its weight. We would also have this upward force that we could call F perpendicular, right? And if that's a flat plane, those are equal and opposite. And so in that case, this F perpendicular, because it's dependent on the angle of the surface, is a good measure to use for a friction force. But it's not just that the friction force equals the perpendicular force, but that it depends on the surfaces that are in contact and also on how much you're pushing on it. So the friction force, we come up with this formula, Ff is less than or equal to mu times F perpendicular. And this thing is called the Greek letter mu. mu. So not, it looks like a u, but it's not. It's a mu, and you know, you could see it in like Microsoft Word as that loads up. I'll show you what it looks like on that, Greek symbol wise. But it's also less than or equal to, because you could push very lightly on something and it doesn't even move, and there's a friction force that's holding that in place. And then you could push very hard on it, and that friction force would go up to a certain level. So I was going to, let's see, insert here a symbol, and the symbol, there it is. There it is. Let's see if we can make it a little bigger. So that's what it looks like in Calibri and Microsoft Word. We made it something different, like, let's say, Times New Roman. It looks slightly different, but it has that little downward slide and then an upward. So mine vary in their appearance, but in general it looks like that. And this coefficient mu, or this mu, is called the coefficient of friction. The coefficient of friction is going to be based on what the surfaces are in contact, and it can be experimentally measured, and we will do that in lab. In most cases, mu is between 0 and 1, although at times it is greater than that. Okay, there are separate values for mu for static, whether it's the static meaning stationary. It's not, the objects aren't moving, but there's a push force, so there's a friction force. There's that, or you could just have a box sitting on a plane. That would be static coefficient of friction. But if you get it moving, the object moving, then it becomes a kinetic coefficient of friction, and that's different than the rolling. So a ball rolling would have a rolling coefficient of friction. So you could have static coefficient of frictions, and also kinetic. And rolling. Coefficients. Okay, some of these, we'll measure some of them, and at other times you'll be given them for problems. So how do we go about measuring coefficients of friction? Well, we'll get some experience in lab. But let's talk about them here. One method is called the hanging mass method. So let's say we had a table, and on that table we have this red block. Okay? We'll give that a little m for its mass. It's connected through a pulley, so this is a pulley here, around a rope to another hanging mass, which will be green, and we'll call that capital M. Okay? So let's first start with some free body diagrams. Let's do the free body diagram for the M, the little m, the red one. And that would have weight force, right, down, Fg for it, which would equal mg. And it would have F perpendicular up, which would be equal and opposite to Fg. It would have the friction force on it, Ff, against its motion. And it would have a tension force, Ft, from pulling on the rope. Now the green one would just have two forces. It would have Fg and F tension. Now if we get this to just be just before it begins to move, okay, right before it starts to move, Fg is going to approach Ft, okay, so that they become equal. Consider them equal, and we get it to a point where it's just beginning to move. So let's look at some of these. Well, we know, first off, the friction force in the red one here is mu F perpendicular. And we also know that F perpendicular is m times g, little m in that case. Now, just as they start to move, we also know from the sum of the forces equal to 0 that, because they're just starting to move, that the tension force in the string will equal the friction force. Okay? Which allows us to say that since the friction force is mu m times g, that Ft equals mu times m times g. Now let's go to the green one. In the green one, Fg is big M times g, and when they just start to move, Ft equals Fg, Ft equals big M times g. Now the thing about this is that the tension in the rope is the same. So we could set these two equal to each other. And when we do that, we get the Ft equals Ft, and that gives us big M times G equals mu times little m times G. The G's just cancel out. And if we solve it for mu, dividing little m over, we can see that mu equals big M over little m. Big M was the hanging mass, and little m was the mass on the table. And so that's one way of calculating mu, is just to put a mass on there where it just starts to move, and therefore calculate your coefficient of friction. Now, one way to do that is sand in a cup. You slowly add sand to it. Maybe just a little bit of sand for very slippery surfaces, and it moves, and maybe for very sticky surfaces, our measurement of sticky is mu. So as we add more and more to the hanging mass, and eventually it moves, and we can calculate our coefficient of friction. Well, that's one way. Another way is on the ramp method. And in the ramp method, we'll use, again, free body diagrams. So sitting on a ramp, angled at theta, we have a block, okay? And if we think of the forces on that, well, we would have our Fg downward, that way. We'd have F perpendicular, and we're going to bring the ramp just till it moves. And when it just starts, till the block just starts to move. When that happens, our friction force that's there is just equal to the component of gravity in the plane, which we call the parallel force, okay? So the sum of the forces equals 0, so F parallel equals FF. Now you can remember what F parallel is. It's Fg sine theta. And friction is mu F perpendicular, but F perpendicular is mg cosine or Fg cosine theta. So what happens is the FG's cancel, and if you divide the sine theta over, divide the cosine theta over, mu is sine theta over cosine theta. Now it happens to be, because sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. The hypotenuses cancel, and you get opposite over adjacent, which is tangent. So mu is actually, sine theta over cosine theta is actually tangent theta. And so we have this other equation. If you lift a ramp up and you get the block to just start to move, where F parallel equals the friction force, mu is equal to tan theta, and you can do that by slowly raising the board until the block just begins to move, measuring the angle and measuring the coefficient of friction. Okay. Here's a friction example. Force of 50 Newton is used to push a 20 kilogram block forward at constant speed. So in that case, there's our block. We have F perpendicular and Fg, and we have the friction force. Sorry. The push force and the friction force. And now we can go ahead and calculate the coefficient of friction. Now in this case, we're just going to use the fact that the push force equals the friction force, and we're given that it's pushed with 50 newtons. So we know this is 50 newtons right off the bat, and the friction force is mu F perpendicular. Well, since it's flat, F perpendicular equals Fg. So in that case, F perpendicular would be 20 times 10, or 200 newtons. So we bring that over, and put that into here. We get 50 newtons over 200 newtons equals mu. Mu is unitless, by the way, coefficient. And, well, 50 over 200. I went to get a calculator, but it's obviously 0.25 is our mu for that problem. Another example is a force of 50 newtons used to push a 20 kilogram block forward, but this time it has an acceleration of 1.5. What's the force of friction on the block? So this actually involves the next unit that we'll do, but put it in here anyways. In this case, we have a push force that's bigger than the friction force back. Same F perpendicular and the same Fg. So in this case, we have the second law, and the fact that the sum of the forces isn't zero, it's m times a. And we have a winner minus a loser, or a push force minus the friction force equals the mass times the acceleration. Okay, so let's see what we got here. Well, we know the push force, that was 50 newtons, minus the friction force, which is mu times F perpendicular, which is 200 newtons from the last problem, equals the mass times acceleration of 1.5 meters per second squared. Okay, so 20 times 1.5 is 30. So we have 50 newtons minus mu, 200 newtons equals 30 newtons. Subtract the 50 over, mu minus 200 newtons minus 50 is minus 20 newtons. So mu would equal 0.10 in that case. And of course it would be less, because in this case, if we think of it as like a coefficient of stickiness, this coefficient of friction Well, if we did the same push, but this time instead of having no acceleration, we got an acceleration, then we would have to have less stickiness and a coefficient of friction of 0.10. Another problem, a 10 kilogram block on a board begins to slide, and it begins to slide when the angle is 37 degrees. What is the coefficient of friction? Well, in that case, we can just do mu is tan theta, mu, because it just started a slide, tangent of 37 degrees, 0.75, and we got the work there. And that's it for